During these meetings, we always like to have maintenance presentations associated with our warning systems. And Mark Moore, who's a system specialist with Distinctive AFWS Designs Incorporated. Sorry, I had to get that one. Has stepped up to give us a presentation on one of the more important things, batteries. So Mark, I will give it to you.
All right. So I started sharing my screen. I hope everyone can see it.
We can see that.
Perfect. All right, thanks, Ron. So yeah, my name is Mark Moore. I work with Distinctive AFWS Designs. And I'm going to spend the next 20 or so minutes talking about batteries. And, you know, I think it's a testament to the conversations we've been having today of all this new technology and new ways to understand what's going on with the meteorology. What I'm going to do is take a complete step back and really go back to the very basics, which is Batteries 101. And this is a talk I've kind of done before. It's one I like to give. I had intended to do this talk actually as a hands-on experience. So knowing that this is a remote conversation, it's not going to work as well. I will try to keep it interesting. I will try to keep the 20-minute conversation we're about to have of batteries engaging and have information in there that's going to be helpful for everyone who might be using batteries in their system. The other thing I want to mention is that there are probably people in here who are experts with dealing with this, with power systems, with batteries. And then there are some people of, you buy a battery off the shelf and you put it in there and you hope it works. And this talk is kind of designed to give information to both, but as the title kind of gives away, it's more of an introduction to batteries. So here's what we're going to talk about. We're going to talk about how batteries work, just the very basics. We're going to talk about what all the numbers mean. If you buy a battery, you'll see it's 12 volts, 20 amp hours, certain Cs, all this stuff. We're going to talk about what those mean. The bread and butter of this conversation is going to be how we're testing batteries and battery maintenance. And then at the end, I'm going to have some time for some final comments. Just a quick disclaimer. I want to be honest with you guys. Most of this information, a lot of the graphs you're going to see are pulled from a PowerSonic, which is a manufacturer of batteries. It's pulled from their manual. It is a really, really good manual. So if you have any follow-up questions, or if I went a little too fast and you want to learn more about batteries, it's worth a read. It's actually, most people don't spend their afternoons reading manuals, but it actually is a pretty good manual to read through. So if you have some time and you want to know, I'd check it out. So these are some very, very basic, broad terms to know when we're talking about batteries. These are some of the acronyms you're going to see. They'll come up in this presentation. If you have a battery on your desk, you're going to see most of these on there. The first one is AH, or amp hours. That's kind of the size of the tank for the battery. It's how big the battery is, it's how much storage it has. The next letter, C, is for capacity, which is actually a little bit of a confusing topic. I'm going to get to that later, I promise, so just keep that in your mind. When C is used when talking about batteries, it's actually used to talk about how fast the battery is being discharged. So C is actually a capacity rate. And again, we're going to talk about this in a little bit. V stands for volts. That's the potential of the battery. That's kind of how much power it can put out. But power in terms of, the analogy often puts it with water pressure. So it's kind of how much strength the battery has in some ways. And last is DC, which is direct current, which happens just to be the type of electricity that these batteries provide. A few more terms to know. A cell is a building block of a battery. Most batteries that we deal with have 6 cells, so 6 times 2 volts is 12 volts. So a 12-volt battery has 6 individual cells in it. Discharge, when I say that I'm discharging a battery, what that means is that I'm drawing current from it, is that I'm using the battery and it's pulling some amount of current out of that battery. A cycle is a charge and a discharge run of a battery. So it is an emptying and a refilling of a battery, or a refilling and an emptying of a battery. That's what a cycle is. And sulfation is the last term that I'm going to discuss. That's what happens when a battery starts to die. It's one of the ways batteries go bad. and it's the formation of lead sulfide on the battery plates. And when that happens, batteries start to lose their efficiency, mostly in terms of their capacity, their ability to store power. So this is just a little diagram that shows what's happening when the battery is being discharged. So again, if the battery is being discharged, that means the battery is being currently used. And basically, the sulfuric acid is being consumed, and you can kind of see how the reaction goes here. Now, this isn't a chemistry lecture, and I'm not going to test, valence electrons and where power is coming from. Why I wanted to show this is because I wanted to show that it is a lead acid battery. So you have lead plates and lead dioxide plates, and then it is in sulfuric acid, which is H2SO4. And so when it's being discharged, it's a chemical reaction that goes in one direction that provides electricity. And when it's being charged, it's just taking that chemical reaction in the opposite direction, and it is storing electricity. So all this is a really basic chemical equation, and it's just using lead, it's using sulfuric acid, and then there are some byproducts that happen in there, like, there's water in there, there's some oxygen gas in there, there's some hydrogen gas in there, and that's just byproducts as this chemical equation goes back and forth. I mentioned voltage, and this is a often used way to know how full a battery is. And I'm going to come back to this graph because it's a little deceptive, and I want that to be clear. So if you take a voltmeter and you put it on a battery, it's going to read hopefully somewhere between 11.8 and 13 volts or so. What that is an indication of is the percent rated capacity of the battery. So if you can see my mouse, if you go to a site and you put your multimeter on there, your voltmeter, and you get 12.6 volts, well, you know that that battery is just under 80% capacity. And so the numbers to kind of pay attention for this graph is that a dead battery, an empty battery, is between 11.6 and 11.8 volts. And a fully charged battery is close to that 12.8 to 13 volts. So the cool things about batteries is that they're kind of like a gas tank. They can provide you power forever as long as you keep refilling the gas tank. You can charge a battery, get whatever electricity you need out of it, and recharge the battery. And theoretically, you can keep doing that over and over and over again, kind of like a gas tank in a car. However, if we do this analogy too far, we start to see some breakdown. So what are the problems with comparing it straight to a gas tank? Well, if you drain that gas tank too fast, so if you're discharging the battery too quickly, what's going to happen is it's going to start to vent gases, because otherwise the battery might get really, really damaged, such as exploding. And as it vents those gases, you're effectively losing capacity of the battery. Another thing that happens over time with high temperatures or just age of the battery is that sulfation I mentioned earlier. And so what that means is that the battery becomes less effective over time because there's not as much place for that chemical reaction to occur. And so, if we're talking about that gas tank with that analogy, it's almost like if every time you fill up your gas tank when you're driving your car, you put a marble in the tank. And the first time you do that, it's not going to do much. But eventually, your gas tank might end up being more marbles than it is gas. And so I've taken that gas tank from the previous example, and I put something that's easier for hydrologists like ourselves to understand. I put a staff gauge on it. So imagine a gas tank with a staff gauge. And that staff gauge will tell you how high the water is in that tank, just like a staff gauge will tell you how high the water is in a creek. What it doesn't actually tell you is it doesn't tell you how much fuel is in the tank. Because if that tank is full of marbles, it's going to be able to hold a lot less fuel. And so that staff gauge is actually just like voltage. The voltage will tell you how high the fuel level is, but it won't actually tell you the volume of the fuel in the tank. So when we looked at this graph earlier, and I pointed out that 12.6 means that your battery is 80% full, all that really does when we're looking at this gas tank is it tells you that 12.6 means that the gas tank level is 80% up. It doesn't actually tell you the volume of the tank, and it doesn't actually tell you how many marbles are in the tank. And a clear way that I like to understand this is to compare it to water pressure. Because again, I said at the beginning of the presentation, voltage is a lot like water pressure. And here you can see three examples where there's water in a container and it's 3 different size containers. But at the bottom of that container, it's the same pressure because the pressure of the water only depends on the height of the water. It doesn't depend on the actual volume. And so this could show, in a way, if you want to think about it, what happens to a battery over time is that you start out with a really big volume and you can get 3 kilopascals as pressure. And then you get lower volume as the battery starts to sulfate or as it gets old. It's the same pressure, it's the same voltage when it's full, but it just doesn't have as much water in the tank. And then even in this extreme example, as long as the water is the same height, as long as you've charged it with enough potential, it will still read as full, but it just doesn't have as much water in the tank. And so, the natural question from there is, well, if voltage doesn't tell me how much water is in the tank, how can you tell? Because voltage only says how high the gas is. So what we care about is the volume specifically, not just how high it is, but we care about the volume. And so the only way to truly do that is to empty the tank and see how much water comes out. And this is not how you'd want to do it with a car, but the idea is you'd be doing a discharge test. So if you take a battery and you know the capacity of it, say a 12 amp hour battery, you can discharge it and you can measure exactly how much electricity is discharged from that battery. And most manuals say that as long as you're still getting 60% of the rated capacity, it's considered a good battery. Now you want to do this discharge pretty slow, on the order of at least 8 hours, but potentially even up to 20 hours. But the idea is slowly discharge the battery, and if it's a 12 amp hour battery and it puts out 10 amp hours, you're okay, that's a good battery. But if it's a 12 amp hour battery and it's only providing 3 amp hours, you know that that battery has effectively lost most of its life. I mentioned I was going to talk about C, and this is where we're going to come back to it. So C, and more appropriately, it's known as the C rate, or the charge rate, or the discharge rate. What it is it's used to express discharge, using, if you're discharging a battery, relative to its capacity. And I keep using 12 amp hour batteries is because that's kind of the standard for an alert or an alert to gauge when all it's doing is reporting data. So you'll see 12 amp hour batteries, fairly common, but any type of battery could be used in this example. With a 12 amp hour battery, if it's being discharged at 0.1 C, that means it's being discharged at 1.2 amps. So at 0.5 C for a 12 amp hour battery, it'd be discharged at 6 amps. For 3 C, which is pretty impressive discharge for a battery, it would be discharged at 36 amps. So just to kind of follow along at home, what would a 100 amp hour battery discharging at 0.25 C discharge at? And I made the math really simple, so everyone can do this in their heads. A 100 amp hour battery discharging at 25 C is discharging at 25 amps because it's 0.25 times the capacity, or 25% of the capacity. Why we care about C rate? I mean, it's kind of a confusing way to talk about discharging. Why don't we just say it's discharging at 25 amps, Mark? What was the point of expressing it in C? And the reason we care about the C rate is because batteries, regardless of their size, have similar characteristics at relative discharge rates. So let me give an example of that. If you're discharging a battery, its final discharge per cell, and remember that a 12 volt battery has 6 of these cells, that final discharge when it's empty actually depends on the discharge rate. So if you're discharging at 0.1 C, or 10%, then it's going to have a final voltage in each cell of 1.75. If you're discharging it at 3 C, it's going to have a final voltage of about 1.37. And the reason that we're using that in terms of C is because it doesn't necessarily matter how big the battery is. That's true for a 2 amp hour battery you might have on your desk for testing. It's true for a 12 amp hour battery that you have at a gauge. It's true for a 100 amp hour battery that you have on a flasher remote site that has to be able to run flashers for a long time. The way a battery performs is almost always relative to the charge, relative to its own capacity. So we mentioned this gas tank and the fact that it could be emptied and refilled and emptied and refilled. One way that analogy really starts to break down, where that analogy just doesn't work as well anymore, is when you're discharging it at higher rates. So this is a chart that I pulled from the PowerSonic manual. And you can see that I broke it down to again, our standard battery, a 12 amp hour battery that is discharged at 0.6 amps will have about 12 amp hours of capacity. Well, that makes sense. Okay, I can accept that. What gets interesting is that if you're discharging that battery at 2 amps, the capacity is actually down to 10.5 amp hours. And if you're discharging that battery at 7 amps, that capacity is actually down to almost 7 amp hours. So it's almost like the size of the gas tank is actually dependent on how fast you're emptying it, which just doesn't make sense. At this point, the analogy's kind of gone out the window. But the important factor here is that, you know, if you're really, really abusing your batteries, not only is it hurting the batteries, it's actually going to provide less overall electricity than if you were discharging it slowly. So here's an interesting chart that kind of shows that same thing. That 0.05 C right here, it goes on for about 20 hours before it's reached that dotted line, which means that the battery is empty. If you were discharging it at 1 C, so for a 12 amp hour battery, discharging it at 1 C would be pulling 12 amps. Let's see where it goes. We follow this line, and it's discharged itself in just 20 minutes. What if we were discharging it at 3 C? A battery discharged at 3 C empties itself in 6 minutes. And so effectively, it's not having as much storage because of how hard you're abusing that battery. And again, this is true for any size battery, whether it's a huge 100 amp hour battery or just a little 5 amp hour battery. Wait, there's something else useful there that I wanted to point out. And so let's go back a slide. Let's look at this chart just a little bit closer. So one thing you also notice is that as soon as you put a load, whether it's 0.05 C or 2 C, once you put a load on a battery, that voltage drops. And pay attention to where the 0.1 and the 0.2 C are. When the battery is still fully charged, you're looking at about 12.5 to 12.3 volts. And we can use that when we're in the field. Because when you're on a site and you want to know if a battery is working well or not, you don't have time to fully empty a battery over 10, over 20 hours. What you want to do when you're on site is you want to have an immediate understanding of, can I trust this battery to work or not? And so we can take advantage of that last chart to do exactly that. We can do something on site to test that a battery works the way it should and get an understanding of its performance. Now, at the end of the day, if you want to know if a battery is working or not, you need to do a discharge test. I'm not saying that this is an alternative to discharge tests. But what I'm saying is that this is a way to field check batteries to make sure they're working okay. And so in this example, I'm going to use a 100 amp hour battery because it just makes the math a whole lot easier. So at 0.1 C, as we mentioned earlier, that's going to deliver power at about 12.5 volts. And at 0.2 C, it's going to deliver power at about 12.3 volts. So if we have that 100 amp hour battery and we put a 1 ohm resistor, Ohm's law would tell us that we're drawing about 12 amps. So 12 amps is a discharge rate of 0.125 C. So if we place this resistor on a battery, if we place a 1 ohm resistor on a battery, the voltage is going to drop to about 12.4 if the battery is working well. If we leave it on there for about 5 minutes, it shouldn't drop much more than 12.4, and when we pull that resistor off, it should go back to where it started. So let's look at an example of that. Let's say the battery starts at 12.8 volts. You've pulled it off the solar panel, it's on the bench in front of you, and it's 12.8 volts. You put that 1 ohm resistor on it, and that voltage falls to 12.35. You let that resistor sit for 2 or 3 minutes, then you pull it off. In the next 5 minutes, the battery is back to 12.77. So it went from 12.77 down to 12.35 during the test, which is a drop of 0.42 volts. And it started at 0.45 higher than that. So it recovered 93% of its capacity. That's a pretty good battery. That would be a trusted battery. And the math can be a little confusing there, but again, let me give it in terms of a use case example. If you have a appropriately sized resistor in your tool bag, and you go out there, you put that resistor on that battery, and I've seen this before several times, where that battery voltage drops to 11.2 11.6, when the battery was just at 12.8. Well, a good battery being discharged at 0.1 C should never drop to 11.8. So that's a sign that that battery needs to be brought in, it needs to be discharge tested, and chances are that battery needs to be fully replaced. One last lesson when we're talking about doing these types of tests. So I mentioned a 100 amp hour battery. If it's drawing 13 amps through a 1 ohm resistor, the power equation is I squared R, so that would be drawing 170 watts. Now those little resistors you've seen for electronics are typically quarter watts, not 170 watts. So if you're doing this test with a battery that is 100 amp hours and you're drawing 13 amps from it, you need a bigger resistor. So this is an example of a bigger resistor that does just that. Another thing to take into consideration is that 170 watts is going to get pretty hot. You're not going to want to touch it immediately after the test. Imagine one of the old incandescent light bulbs. They are 60 watts. You wouldn't want to change one of those after it had been on for a few hours. It's the same thing. This is going to get pretty hot. The other thing I want to make sure is pretty clear about this is that you want to discharge the battery at approximately 0.1 or 0.2 C, or 10 to 20% of the capacity. So for a 100 amp hour battery, that means you want to be pulling 10 to 20 amps. For a 12 amp hour battery, you only want to be pulling about 1 amp. And so if you have this big old 100 amp hour battery, you can't just draw a little bit of power. You need to draw a pretty substantial amount of power from that battery to truly do the test, which is why there's this big old resistor. If you have a smaller battery, you can do some sort of smaller power draw, whether it's a smaller resistor or even just hitting the transmit button to see, do something that draws about an amp, and you'll be able to see the change. But for the bigger batteries, you really need a bigger power draw. So I also wanted to talk a little bit about battery life. This is something that I've seen agencies have a lot of questions about. Kind of, why are my batteries dying, or what can I do to keep my batteries lasting longer? What's the best way to take care of a battery? So one thing to be aware of is that deeper discharges ruin batteries faster. If you're emptying your tank all the way, you're effectively adding extra marbles to it every time you empty it. And so this graph is showing you that the capacity, 60% capacity is about when a battery fails according to the manual. And so if you're discharging at 100%, if you take that battery and you fully charge it and you fully empty it and you fully charge it and you fully empty it, it's only going to last about 200 to 300 cycles before it's dead, before it's gone. If you're discharging it 50%, if you're only taking it halfway down, it's going to be able to do that almost 500 times. Now, if you discharge it only 30%, so you fill the battery up and you just bring it down a little bit, and then you refill it and you just bring it down a little bit, and then you refill it, it's going to last up to 1,000 cycles. And so ideally in your systems, you don't want to be 100% discharging your batteries, because every time you do that, you've shortened the lifespan of the battery. For most gauges that are just doing something like transmitting data, it's probably going to fall into this field, where it's just not going to discharge it very much. But if you have something malfunctioning, or if you are powering flashers or signs or cameras that take a lot of power, you might get closer to this range. And so you might only get 200 cycles out of it. However, if it's something like a flasher, it might only activate 1 or 2 times a year. So this is an important graph to look at and to consider when you're thinking about which type of battery you're putting in a site. A little bit more about battery life is that battery life is very, very dependent on what temperature it's at. So if you keep your batteries at 30 degrees, which is about 30 degrees Celsius, that'd be about 80 degrees Fahrenheit, 85 degrees Fahrenheit, most of your batteries are going to last between 5 and 7 years. If you're keeping your batteries at 40 degrees, about 100 degrees Fahrenheit, you're looking at 3 to 5 years for battery. And if you're keeping your batteries at 120 because they're in these stainless steel cabinets and it's really hot and it's on direct sun, your average battery might only last 2 to 3 years. So you want to keep batteries as cool as possible to maintain their life, to have them last as long as possible. In terms of storing batteries, you have your batteries that are out in the field, but you also have your batteries that you have on your storage shelf. For storing batteries, your best practices are to keep them cool, keep them charged, and keep your batteries tested. So anytime you purchase a battery, it's worth go ahead and and run it through the test cycle just to make sure it's good from the factory. And doing that first discharge and charge cycle is actually pretty good for the battery's health. Just the initial one. So this is showing storage of the battery, just what we were talking about. And it shows what happens to batteries' capacity on the shelf dependent on temperature. And so if you happen to have, I don't know, an industrial freezer on your facilities, and you put your batteries in there and it's 30 degrees Fahrenheit, that battery is this top line. And after 18 months, it's still pretty full. But what if you have a warehouse and it gets to 100 degrees all the time? That's this bottom line. If that battery is kept in a hot warehouse, after 6 months, you've already depleted half of the battery. You're going to pull that battery off that shelf and it's going to be half empty just because of how hot it was. And if it's been empty for that long, it might not ever reach full capacity again. And so something to consider about how you're storing your batteries is always try to keep them, if possible, inside, air conditioned. You want to keep them cool, and you want to charge them up every 6 months or so. When you are charging a battery, the current should drop off once that battery is approaching fully charged. So this graph kind of shows as the battery is being charged, the voltage of the battery is going to go up as it gets charged, and then it'll reach this cap. You want your charge current to be steady through that initial charging and then taper off. Nearly every battery charger out there is smart enough to do that. Just be aware if you ever tried to straight power supply it, you might not be charging it as effectively as possible. What you really want to be doing is putting into a smarter charger. So some do's with batteries: you always charge depleted batteries as soon as possible. If you go out to a site and you find a battery that's at 10.5 volts, you need to get that on the charger as soon as possible, because the longer it's kept low, the more likelihood of permanent damage there is for that battery. You should charge shelf batteries every 6 months. If it's been sitting there at room temperature, you want to keep it topped off, and you want to keep it topped off by making sure at least every 6 months it's put on the charger. As I mentioned, store batteries cool, charged, and tested. You want to charge and discharge as slowly as possible. And you want to charge those rapidly at 14.7 volts, and then you want to float that down to 13.6 volts once it's fully charged. And again, that's just a factor of a smart charger. The don'ts for batteries: never charge a battery in an airtight enclosure. There is a potential for dangerous gases to build up, and it's not a good safe practice. Never use a battery that appears damaged, and I'll show you what I mean by that next. Don't exceed 14.7 volts when you're charging. Never let the battery drop below 10.5 volts. Again, that's kind of the point of no return. A battery that's gone that low, it might come back, but it might not. And as I mentioned previously, you can't just use voltage as battery health. You've really got to do a full test. Just to show you what I meant by damaged battery, this is often what you'll see when batteries have become damaged by heat or something else has occurred with the venting process, where this is a normal battery, this is a good battery, this might be what you want to see, and then when it's been damaged, it's become bloated. Batteries are not worth putting out in the field. If they look like that, they're not that expensive. At that point, recycle the battery, get a new one, and put in something that you can trust to work during an emergency situation. Some common misconceptions that I've seen a lot when it comes to batteries. Myth: I can check the voltage to know if the battery is good or not. Truth: the voltage only tells part of the story, and the discharge test is needed to get the complete picture. I know I've kind of hammered in this point, probably too much at this point, but I've seen it a lot where people will grab a battery off a shelf and they'll read in, okay, the battery's at 12.7 volts. That's a good battery. I can go put it in gauge. And that's not necessarily true. You don't know that the battery is a good battery unless you've done a full discharge test. You can know that the battery thinks it's full, but to really understand if it's a good battery, the voltage just doesn't tell you enough. You've really got to do a full test. Myth: I should always have a backup battery in my truck or toolbox. Okay, that one's mostly true. But remember what we said about storage. If that truck is parked out in the sun and it's 120 degrees inside that metal toolbox, that battery is going to lose its capacity and start to get damaged in just a month or two. So try not to let the battery that you keep as backup get too hot. Try not to leave it in the truck during the weekends. Keep it topped off. If you have a spare battery, which you always should, make sure it's a good battery that you trust, that hasn't been sitting in your truck for the last year and you haven't looked at it since then. Myth: a site that has a low battery voltage probably has a bad battery. Truth: it might be a bad battery, but you should never just swap a battery because the voltage was low. You should look at what caused it to be low. Maybe there's a component that's malfunctioned and it's causing extra current drain. Maybe the solar panel's not working, or it got shot, or someone decided to steal the solar panel, and that's why the battery voltage is low. So battery voltage being low is a sign that there's a problem at a site, but it's not necessarily a sign that there's a problem with the battery. You have to kind of put on your troubleshooting thinking cap and figure out why the battery got to the point where it's at. And it could be because the battery just reached end of life, or it could be something else going on at the site. So just some very brief final thoughts. Batteries aren't complicated, but misunderstandings can cause troubleshooting to go in the wrong direction, and that wastes time. So it's really worth understanding how batteries work and the useful numbers when you're looking at the specs, and how those apply to using batteries in the field. And I think this is important both for technicians who are out there in the field and they're trying to figure out why a site keeps draining batteries, but it's also important for system managers so that they understand, well, why did I have a battery die 4 times at the one site? No, that shouldn't be happening. There's something wrong at the site. So I think at least a basic understanding of batteries is worth it for anyone who deals with flood warning, because it's going to be impactful for your system performance. And as we've stated several times now, these gauges have to work for any type of emergency situation. And so making sure that every component is as trusted as possible is just incredibly vital to having a good working system. I wanted to share a link to where you can download the PowerSonic manual. I don't think many people are going to go do it, but it's worth a read. It even has a section for notes in the back. There are other great manuals out there regarding batteries. I just know that this has been one of the best resources that I've used. And with that, any questions?
That was great, Mark. A lot of good analogies there. We'll give it a minute, see if any questions come in.
I know it ends up being a bunch of information at once, but like I said, it's really important to make sure that those components are working right. And I've seen those mistakes get made, and once people understand, they're usually happy to do things the right way. So.
So
we did get one question. If I could post a link to the PowerSonic manual in the chat, and I will be happy to do that. So I will send that along when I have a chance.
Excellent. All right. Thank you, Mark. Oh, wait. One more just came in.
All right. So the question that came in was, what are my suggestions in regards to load tests, and are these helpful? So, I think a load test should be part of visiting a site every 6 months. I think that they're incredibly helpful and that they're really important to do, but I don't think it replaces doing a full discharge test. I think a load test is more of this is what I can do while I'm on a site, whereas a discharge test is actually testing the battery. And the other thing, as I mentioned with load tests, is you've got to make sure that you're drawing the appropriate amount of current. Because if you're just drawing a little bit of current from a big battery, then there's no purpose for a load test. So load tests are really helpful. It's really the only way to get a good idea when you're up on a mountaintop and 30 miles away from a power plug to do a discharge test. But they don't always tell the full story. All right, thanks everyone.